now we will be discussing another example of Ancova analysis. This time our experimental variable has 3 qualitative levels. So we change the experiment. This time our experiment is about growing beetroot. Since Christmas is coming, and beetroot soup is one of the traditional dishes for Polish Christmas, therefore it is an appropriate experiment to be thinking about now. The experiment is performed in order to assess 3 different types of fertilizer. We have the dependent variable, which is the yield of a field. Sorry, there is a misprint. Yield of a beetroot field in pounds of the product gathered from the field. And there is a covariate, which is nitrogen level in the soil. Nitrogen level expressed in pounds per acre. This information is important for plant growing. However, of course it can be controlled by using proper fertilizer, but in this experiment it is not controlled, it is measured. And we have 3 types of fertilizers encoded in numbers 1, 2, and 3, and these are values of experimental variable 3. We proceed as before. We look at the scatter plot. This time we see that there is clear linear dependence between yield of the field and nitrogen level in the soil. However, when we look at colors, we have here color-coded types of fertilizer. We see that the colors are mixed. So looking at the picture, I don't expect significant differences between types of fertilizer. Okay, then we should check for interactions, and here again this is real life data, so we don't have ideally parallel lines. However, the slopes are rather similar, therefore I would say that we can proceed with our analysis. The slopes are not equal but close enough. And again, we see that there is no clear conclusion from the picture, so that some fertilizer is better than the other. The problem now is that our experimental variable is a qualitative variable which has 3 values. Therefore, it cannot be used in multiple regression model as it is. In such a case, we encode our qualitative variable in the proper number of dummy variables, and there is too many m's here. If our variable has say, R values, then we need R minus 1 dummy variables, which means in this particular situation we need two dummy variables, which I denote y3 and y4. We put y3 equal to 1 and 1 and 1 4 equal to 0 for fertilizer number 1. We switch them, so y3 equal to 0, y4 equal to 1 for fertilizer 2, and then we have to put y3 equal to 0, y4 equal to 0 for fertilizer 3. And then the combination of these values gives us three subgroups in our group of subjects. And both variables y3 and y4 are now variables qualitative, but having only two values, therefore they can be meaningfully used in linear regression model. Our full regression model will now consist of three independent variables, which is a covariate x2 and two dummy variables. And our reduced model will be as previously with only a covariate. Therefore, passing from the reduced model to the full model, we add two new variables, which experimental, which will have an influence on the number of degrees of freedom in our experiment. The null hypothesis says that coefficients B3 and B4 are 0, so that there is no difference between the yield of a particular field with the same nitrogen level and different types of fertilizer used. The alternative hypothesis, of course, is just a negation of that. So it says that at least one of these coefficients is different from 0. In this experiment, we will calculate f value directly from definition, so without any additional formulae, just using sum of squares as it is in the definition. So for that, we definitely have to calculate the two regressions, so they are determined, and we calculate the errors. If we have errors calculated, we can look at the histograms of errors. So here is the histogram of errors of the reduced regression, so only with the covariate, and here is the histogram with for the full regression model. Not bad. I mean, maybe they are not exactly normal, but they are reasonably close to normal. And now we pass to the sum of squares. We calculate the sum of squares, and let us look at the final outcome. So we have here reduced model regression, full model regression, and what we are interested in, the p-value. The p-value is large. So as I expected, looking at the picture, we conclude that there is no significant difference between different fertilizers used. Okay, so that's all Let us at the very end underline the difference of this example as opposed to the previous one. In this example, we have three colors here, which means that our experimental variable has more than one, in this case three values, which means that if we want to use Ancova, we have to adapt for that by encoding our experimental variable in two auxiliary variables that are of 0, 1 type, and that can be used in multiple regression.